All right, this video is for deriving the acceleration due to uniform circular motion. Okay. So we are going to imagine that we've got a coordinate system like this, and we're going to do this in Cartesian coordinates and then show why it's easier if we use polar coordinates to do this instead. So we imagine that we have an object here that is undergoing uniform circular motion like this. It's directed counterclockwise, so over time it's going around our circle like this. I'm gonna pick another color that's easier to see. Let's do. Okay, so we've got our object that's moving around. Okay, and we want to start by writing position as a vector, and then we can use that to find the velocity as a vector, and then the acceleration as a vector. So we want to write the position vector as a function of time. So imagine that this is our r at some moment in time. This is, we're going to call this delta theta. It's the angle that it has gone through so far. And so the position at some time then is r is r cos theta. Let me call this delta theta to be consistent. R cos delta theta I hat plus y, no, plus r sine delta theta j hat, okay? And we also know from basic description of arc length that the distance that this has traveled along a particular arc, for example here, is delta theta r, and if it's traveling at some speed v, then it's the distance it traveled is also vt. So we can say that delta theta equals vt over r. So now we can write that this r is, our vectors are cosine of vt over r I hat plus r sine vt over r j hat, okay? And then now we know that v is dr dt. So we're going to take a time derivative of this, and you can remember from your trigonometry that ddt of cosine t, for example, is negative sine of t, and ddt of sine t is cosine t. And then we're going to use that plus the chain rule to find that our velocity is negative r sine vt over r times the derivative of this part that's inside the parentheses here. So that's v over r I hat plus r cosine vt over r v over r j hat. Okay. And now I've just taken, notice I've taken the derivative of each of these terms separately. So this is the derivative with respect to time of the x coordinate, and this is the derivative with respect to time of the y coordinate. We're just going to rearrange these to make this a little bit easier to read. So v then, these r's cancel, is negative v sine vt over r I hat plus v cos vt over r j hat. Now, let's think about the direction of this, or at least the signs, and see if they make sense. So at some moment here, we've I'm gonna draw a new coordinate system down here. We've got our object here. Its position vector is points in this direction here, and its velocity vector at this point should point in this direction. So we've found here that the x component here is negative. That makes sense. It's directed to the left in our picture here. And the y component is positive, which again makes sense. It's going upwards in our picture. And we can also notice that the sines and cosines are flipped because the velocity vector should be perpendicular to our vector, which does indeed make sense. We can also check what is the magnitude of v, right? And that's going to be the square root of v squared sine squared vt over r plus v squared cos squared vt over r. Sine squared plus cos squared is 1, so this is just v. So sounds good. Everything seems to make sense so far. All right. So those are just some checks we can do along the way. And now to find the acceleration, we remember that our acceleration is the time derivative of velocity. So we're going to now take our expression of velocity and take another derivative. So now we've got negative v cosine vt over r, another factor of v over r I hat, plus negative v sine vt over r v over r j hat. And so that's going to give us v squared over r cos vt over r I hat plus sine vt over r j hat. Now notice this part here. Oops, and I've forgot a negative sign here. Sorry, negative sign here outside. So notice this part that I've highlighted in purple here looks very much like our position vector from the top, right? Remember, r was r cos vt over r I hat plus r sine vt over r j hat, right? So this looks the same as that, except that it has a different magnitude. This magnitude is negative v squared over, or magnitude is v squared over r, and there's a negative sign, which means that it's pointed inward. In other words, our acceleration vector is has a magnitude of v squared over r and directed toward the center of the circle. Okay? Just as we said in class. All right. Okay, so that's one way of doing this. As you can see, if you write this all in Cartesian coordinates, it gets a little bit messy, although becomes not actually all that complicated. It just becomes a little bit messy. I want to briefly point out what would happen if we wrote this in circular coordinates instead of Cartesian coordinates. So in that case, our r vector would just be r hat, where now our r hat vector points in the direction of that radius. So this looks like r hat. And theta hat is a vector that we can define as pointing in the direction of delta theta here, okay? So our velocity then points in the direction of theta hat. So we can just write v very simply as v theta hat. But notice that now this theta hat is a function of time, okay? So this is now kind of a weird unit vector because its direction changes at every moment in time. So if we want to write dv dt, that we want to use the multiplication rule for our derivatives, and we would find that this derivative would be dv dt theta hat plus v d theta dt. Okay. Or not, sorry, there should not have been a vector sign there, like this, okay? And then d theta dt, d theta hat dt, we can find is v over r hat, okay? Which we can find from the fact that delta theta is vt over r, as we talked about above, right? And so delta theta delta t is v over r in terms of its magnitude, and then the direction of d theta dt is going to be negative r hat, because it's the direction that it's changing over time is in the direction of r hat, right? So a little bit later, so if we imagine here's our theta hat at one moment in time, and then a little bit later, its moment in time is going to be like this. The change in delta theta hat looks something like this, and that's directed inward, okay? So notice there's this negative sign here that I forgot to write at first, okay? All right, so now we can plug this expression here into our expression for v above, and then we find that dv dt then is dv dt theta hat plus v times negative v over r hat. So that's dv dt theta hat minus v squared over r hat. Now notice here I did not assume uniform circular motion, so this first term here is the tangential acceleration because it's dependent on changing velocity over time. And then this second term here is our centripetal acceleration. Okay. So as you can see, this entire derivation is now on this page once I use circular coordinates instead of Cartesian coordinates. So you can see that often you can really simplify the math when you choose the right coordinate system, as we're going to talk about more as we continue our section on Newton's laws.